Hello friends, welcome to Knowledge Galaxy to rediscover the basics with Mayank Tiwari, a premier coaching and training channel dedicated to metallurgy studies and consultancy. Established to cater the needs of students, degree, diploma and AM/IIM metallurgy, competitive and recruitment exams for GATE, SAIL and various other government and private sector companies, metallurgical industries, working and aspiring professionals and whosoever seeking knowledge and information about various subjects and topics of metallurgy, ferroalloys, operational process optimization, productivity improvement analysis, etc. To impart practical industrial knowledge as per your specific requirements via tailor-made training sessions for your colleagues, employees and students, please contact me on knowledgegalaxy26@gmail.com or WhatsApp me on +919907144101 for scheduling and organizing the sessions at your place or via video conferencing. My dear friends, nowadays technology has improved so much that actual physical distance doesn't matter anymore. You can get all your doubts cleared by sitting at your home, at your comfort zone, just by contacting me over WhatsApp or phone, so that for your benefit, please do contact me for any of your doubts. My dear friends, I have made so many videos which are available on my YouTube channel. So I request you to visit my channel regularly and repeatedly and watch all the videos available there, so that you can gain maximum knowledge about the subject and topics, and also request you to watch all my videos from start to finish, so that you can gain the maximum and complete knowledge about the topic. My dear friends, as you know that training is costly, but not to train is still costlier. And when you are not having complete knowledge or don't get any information about the topic which you need to know, so you can contact me. If you don't find anyone who can help you to clear your doubts, you do contact me as soon as possible. And so right now in this video I am discussing about In this video, I am going to describe about a very much important and practical process of steel making and the route which is used worldwide, and it is increasing day by day. Its application is increasing worldwide, and now it is treated as a very effective and very efficient way of production of steel. So the current topic of this presentation is steel making via the electric arc furnace route. I hope you have heard about this electric arc furnace route, and in the coming slides I will be describing in detail about the process, its characteristics and typical relations, equipments, everything in detail about the steel making via the electric arc furnace route. But before proceeding, I will request you to please watch and observe the video in the next slide.
seen and observed in the video that no water can be filled in the pot if the pot is not aseptic, and also if the pot is already filled. The water can only be filled when there is some space in the pot. So, my dear friends, I request you to keep your minds open for receiving the information so that you can receive the information correctly and gain the knowledge. But if you feel that you are already having much knowledge or more knowledge, or if you are not receptive towards receiving the new knowledge or information, you cannot gain anything. So for gaining new knowledge and information, please keep your mind open and be receptive for the new knowledges always.
So my dear friends, let's start and begin the presentation for today. And to start with, let me first tell you about the main contents and topics which I am going to cover in this presentation. So to start with, it will first start with schematics of electric arc furnace. Then will come history of EAF steel making. Next is the furnace and the auxiliaries. Afterwards, conventional EAF steelmaking practice. Next is advances in EAF steelmaking. Then later on equipments. Then raw materials. Next will be principle of electric arc furnace operation. Next will be advantages of electric arc furnace operation. Next, design of electric arc furnace. Then characteristics and types of electric arc furnace. Electric arc furnace operation. Then the refractories for electric arc furnace operation. My dear friends, I hope by seeing these contents, you might be very much sure that how deep and detailed the presentation will be. So I request you to be patient and observe the presentation very carefully and watch the videos very carefully. And in case of any doubt, or if you have any further queries, you can contact me anytime. My contact details are always available and displayed in the slides everywhere. So whatever is your queries, you can contact me so that I can confirm and clear all your doubts. So let's move on. So this is the schematics of electric arc furnace. So different equipments, their parts, their structures, and how the overall electric arc furnace is designed is depicted here. I know that the picture is not very much clear, but then also it gives a picture and clear idea about the different equipments and accessories of the electric arc furnace. Moving on to next. So this picture is very much clear further, and it describes the various stages of electric arc furnace steel making. The picture is very much clear and self-descriptive. So let us first know the history of electric arc furnace technology for steel making, how it evolved and how it developed. Though Darlevel had patented an electric furnace for the melting and refining iron in 1892, and Herold had demonstrated electric arc melting of ferroalloys between 1888 and 1892, the first industrial electric arc furnace, that is EAF, steel making process only came into operation in 1900. Development was rapid and there was a tenfold increase in production from 1910 to 1920, with over 500,000 tons being produced in 1920, though this is still only represented a very small proportion of the global steel production at that time. Initially, EAF steelmaking was developed for producing special grades of steels using solid forms of feed such as scrap and ferroalloys. Solid materials were firstly melted through direct arc melting, refined through the addition of the appropriate fluxes, and tapped for further processing. Till the late 20th century, tap-to-tap times over 3 hours were common and power usage was frequently well over 600 kilowatt-hour per ton, nearly twice the thermodynamic requirement. For much of the 20th century, EAF steelmaking was viewed as an expensive and slow process only suitable for high-value steels.
My dear friends, just to interrupt you all, here I would like to emphasize on some special important aspect of Knowledge Galaxy. Here, specialized subject-wise coaching classes and topic-wise doubts clearing are available. I am available for all of you to clear all your doubts, and especially for Diploma Engineering, Metallurgy and Mechanical students, Indian Institute of Metals, that is IIM, Part 1 and Part 2, and competitive and recruitment exams for GATE, SAIL and various other government and private sector companies, metallurgical industries, working and aspiring professionals. Here I would like to emphasize that whatever queries and doubts you are having in your mind regarding any subject or topic of metallurgy or any other ferroalloys production, operation, maintenance, so you can contact me for getting your doubts cleared. I will try to provide you accurate knowledge and to the best possible extent at the very shortest period of time, so that you can gain your knowledge, clear all your doubts, so that you can grow in your career, whether it is academic career, whether it is of professional career, and so that you can develop and grow. So to continue with, here complete syllabus coverage for the students aspiring to appear in the forthcoming semester exams, that is December or June. I will be providing you all. So please contact me on knowledgegalaxy26@gmail.com or WhatsApp me on +919907144101 for scheduling and organizing the classes or getting informations to clear your doubts via video conferencing, call or WhatsApp. My dear friends, you might have encountered that you might have been having many of the doubts regarding process, technology, why they are doing, why it is done, how it is done. So, and if you don't find any answer to them and nobody is there to guide you properly, so my dear friends, I am here available to guide you all, to make you know and grow, and so that you don't have any doubts related to your process, products, technology, syllabus, and I will make sure that all of your doubts get clarified and you know the topic and subject very well and completely. So again, let's move on.
EAFs are sometimes classified based on the power supplied per ton of furnace capacity. For several EAFs, the design allows for at least 500 kVA per ton of capacity. There are EAFs which allow 900 kVA to 1000 kVA per ton of furnace capacity. Majority of EAFs operate at a maximum power factor of around 0.85. Hence, the transformer ratings correspond to a maximum power input of around 0.75 to 0.85 megawatt per ton of furnace capacity. The emerging new technology of EAF started in the beginning of the 20th century when wide-ranging generation of relatively cheap electric energy started at that time. First generation electric arc furnaces had a capacity in between 1 ton and 115 ton only. Initially, the EAF had Bessemer or Thomas converters and Siemens Martin furnaces as strong competitors. But its niche was the production of special steels needing high temperature, ferroalloy melting, and long refining times. Initially, for the bulk production of plain carbon steels, open hearth furnaces were less expensive because of their large size as well as the higher cost of electricity. All these started to change from around 1970 because of the following. First, while the cost of liquid fuels started increasing, electricity generation costs became lower and electricity became comparatively cheaper. Next, larger and higher power EAFs could be installed because of the progress in electrical engineering and control systems. Next, EAF steelmaking is intrinsically cleaner than open hearth steelmaking. Next, since EAF steelmaking is predominantly scrap-based, smaller plants with lower capital investments and faster attainment of rated capacity could be set up even compared to BF/BOF based plants. BF is blast furnace and BOF is basic oxygen furnace based plants. Therefore, electric arc furnaces started gradually replacing basic open hearths for producing plain carbon steels as well. With electric arc furnaces ranging in size from 100 ton to 250 ton and even 500 ton capacity, there are some plants around the world which are producing 1.5 to 2 million ton per annum of steel from 2 to 3 large electric arc furnaces. This type of growth in electric arc furnace steelmaking has resulted in scrap shortage. This has been taken care of by partial substitution of scrap by sponge iron, that is DRI or HBI. DRI is directly reduced iron and HBI is hot briquetted iron. And in some plants with additional charging of cold pig and hot metal. Electric arc furnace based operations have gradually moved into production of steels which were traditionally made through the integrated route. The first of these areas was long products, that is reinforcement bars, merchant bars and wire rods. In the 1960s, with the advent of billet casting, the electric arc furnace occupied a new niche and became the melting unit of choice for the so-called mini mills, feeding billet casting machines for the production of long products. This was followed by advances into heavy structural and plate products, and by 1985 a new niche for electric steelmaking began to be taken to the flat products area with the advancement of thin slab casting and direct rolling process. In the following 2 decades, to better support the short tap-to-tap time needed by billet casting machines, the electric arc furnaces reinvented itself as a melting-only unit. Steel refining was left for the recently introduced ladle furnace. Large transformers were introduced. Ultra-high power, that is UHP furnaces were developed, which were made possible by adopting foaming slag practice. This way, tap-to-tap time became close to casting time. Since the 1960s, the technology has undergone rapid development, moving from a boutique technology to the second largest steelmaking technology behind basic oxygen steelmaking, that is BOS technology. Since the late 20th century, the production of steel by the electric arc furnace has grown considerably. There have been several reasons for this, but primarily they are relate back to product cost and advances in technology. In the next slide, figure 1 shows evolution of electric arc furnace technology during the period 1965 to 2010. So this picture depicts the evolution of electric arc furnace technology during this period from 1965 to 2010. So you can observe this picture and get to know what are the different evolutions in the electric arc furnace technology over the period. Moving on, the traditional electric arc furnace steel making process with all or high ratio of scraps as metallic raw materials can result in a higher content of harmful heavy metal elements to deteriorate aimed steel specifications or grades. Hence, the normal flow chart and organization of electric arc furnace steel making can be normally disturbed by charging excessive scraps with complex chemical compositions. It has been widely proposed that one of the effective measures to avoid and solve this problem is to increase hot metal charge ratio. However, excessive charging of hot metal can lead to prolonging the tap-to-tap time of electric arc furnace steelmaking process, since large carbon load from the excessively charged hot metal can overburden the decarbonization operation during the electric arc furnace steelmaking process. As the electric arc furnace steelmaking attempts to further displace steelmaking through the integrated route, several issues come into play, such as residual levels in the steel, essentially elements contained in the steel which are not removed during melting or refining, and dissolved gases, namely nitrogen, hydrogen, and oxygen in the steel. Both of these have a large effect on the quality of the steel and are to be controlled carefully if electric arc furnace steel making is to compete for the production of higher quality steels. So now let us discuss about the furnace and its auxiliaries. Electric arc furnace is a direct arc furnace where the arc is struck between the graphite electrodes and the metallic charge or metal bath. The arc temperature is above 4000 degrees Celsius and is used to heat the bath by radiative heat transfer. The traditional power supply is three-phase AC requiring three electrodes. The modern trend is to go for DC arc. Figure in the next slide shows the cross section of a conventional EAF. So in the next slide, the figure depicts the typical cross section of a conventional electric arc furnace. So you can observe that picture. So then basic type electric arc furnaces are employed for steel making. Hence the inner lining of the hearth in such furnaces is burnt magnesite. Charging is done from the top, and during charging the electrodes are lifted up to allow the roof to be swung horizontally to one side, thus providing open access from the furnace top. So this is the cross section of an electric arc furnace. Here both acid and basic linings are shown for illustration, so that you can know that for the purpose of basic production of steel making, basic lining is used, and for acidic production of steel making, acidic lining is used. I hope this picture is very much clear and self-descriptive. My dear friends, I hope you have observed the cross section of an electric arc furnace shown in the previous slide. So now let's move on, and in the next slide contains a sketch of a typical electric arc furnace shop layout. Electric arc furnaces can be tilted to one side for metal tapping, and slag tapping is carried out through the opposite side slag door, for which the furnace is tilted the other way. the electrodes get worn out and consumed during arcing, and before the length of an electrode becomes too small for operation, another electrode is joined to it at the top. In order to do this, each electrode has internal threading at the ends, and the threaded ends of the two electrodes are connected by a threaded graphite nipple. So this is the vertical section of an electric arc furnace shop. You can see and observe the various equipments installed in the electric arc furnace shop. Now let me describe the whole layout in detail. So the furnace unit itself includes the following parts. First, furnace body consisting of the shell, the hearth, the walls, the spout, doors, etc. Next is gears for furnace body movement. Next comes is arrangement for moving the roof. Next is electrodes with their holders and supports. Electrode lifting and lowering mechanism. Next is electrical equipments, that is transformer, cables, electrode control arrangements, etc. The furnace shell is made by welding or riveting steel plates. Its side walls is cylindrical in shape and the bottom is shallow and bowl shaped. To give you an idea, the shell diameter is about 6 to 6.5 meter for a 100-ton capacity furnace and 5 to 5.5 meter for a 50-ton furnace. So this is a typical idea, need not be exactly same for each and every furnace. It varies. Large transformers are equipped for supplying power to any electric arc furnace. The primary voltage may be 33 kilovolt or more, and the secondary voltage anywhere from 200 volts to 1000 volts depending on the furnace size and power supply. Electrical characteristics of the circuit are schematically shown in the figure in the next slide. I hope you will also like that figure and also observe it very carefully. Since the voltage as well as the power factor decreases as the current is increased, the maximum power is obtained at an optimum current level. So this is the electrical characteristics of an arc furnace during operation, and this is schematic. I hope it is very much clear to you all. You understand the terms everywhere very carefully, very clearly. Next, moving on. My dear friends, I hope we are going so far so good, and let us keep the momentum going and continue the presentation, and let us discuss the conventional electric arc furnace steel making practice, how steel was made in conventionally in electric arc furnace. As mentioned already that the process of electric arc furnace steel making is about 100 years old. Through decades of efforts till 1970, electric furnace steelmaking practice got significantly standardized. This is what is denoted by the term conventional. It is practiced even now in smaller and relatively older units. Electric arc furnace steel making involves most of the stages in heat making in basic open hearth furnaces with the exception of the following. Hot metal is not used in conventional practice, my dear friends. I repeat, hot metal is not used in conventional practice. The refining and finishing practices differ widely. The basic purpose of refining in electric arc furnace is twofold. First, removal of undesirable impurities, that is carbon, silicon, phosphorus, sulfur, nitrogen, hydrogen, etc. Next is finishing the bath so as to ensure maximum alloy recovery. Electric arc furnaces produce a wide variety of steels. Therefore, depending on the type of the solid metallic charge and the grade of steel to be produced, the refining practice differs considerably. The type of refining employed may be broadly classified into the following. First, oxidizing single slag practice. It is employed to produce tonnage grades of carbon and low alloy steels as well as non-deoxidized, semi-deoxidized and deoxidized steels. The physical and chemical specifications are not very stringent. That is, the quality of steel is similar to what is attainable in open hearths using a basic oxidizing slag as the medium of refining. Next comes is double slag practice. In this case, after refining using an oxidizing slag, further refining is carried out under a reducing slag. So I hope this term double slag practice is clear to you. So let me again repeat this. Double slag practice, in this case, after refining using an oxidizing slag, further refining is carried out under a reducing slag. The reducing slag allows attainment of lower sulfur levels and also assists in higher alloy recovery after tapping. In this practice, the original oxidizing slag can be modified by the addition of reducing agents. However, it gives rise to danger of reversion of phosphorus from the slag back to metal. To preclude this possibility, generally the oxidizing slag is completely removed and fresh reducing slag is made by charging lime, fluorspar and silica. The reducing agent may be graphite or coke grease. This type of slag is commonly referred to as carbide slag since the carbon added reacts with CaO to form some amount of CaC2. Carbide slags do not allow very low carbon contents to be attained in the bath. In such cases, ferrosilicon is used as the reducing agent instead of carbon. The typical compositions of slag are shown in the next table. So it will also help you to understand the slag compositions very carefully and very easily. So this is the slag compositions used in two slag practices in electric arc furnace steel making. So this table gives the idea what are the constituents of various slags in during this two slag practice in electric arc furnace steel making. You can observe this table by pausing the video. Okay, let's move on. At this stage, it is worth noting some salient differences in the metallurgical features of basic open hearth and electric arc furnace steelmaking. These are noted below. First, since electric arc furnace steelmaking is primarily scrap or DRI based and both these materials have relatively low levels of residual impurities, the extent of refining is much less than in basic open hearth steelmaking. As a process, electric arc furnace is far more versatile than basic open hearth and can make a wide range of steel grades. Sorting out of scrap and choosing the proper scrap grade are important for electric arc furnace steel making. This is the heart of the steel making operation via electric arc furnace since the extent of refining has to be managed accordingly. For this purpose, scrap may be classified into the following categories. First is scrap containing elements that cannot be removed by oxidation during refining, such as copper, nickel, stannum, molybdenum, tungsten, etc. Next category of scrap is scrap containing partially oxidizable elements such as phosphorus, manganese, chromium, etc. Next category of scrap is scrap containing completely oxidizable elements such as aluminium, silicon, titanium, vanadium, zirconium, etc. Next category of scrap is scraps containing volatile elements such as zinc, cadmium, plumbum, etc. Now comes scrap of type B and C can be tackled easily during refining, and type D scrap would require some special attention. However, type A scrap gives rise to problems like undesirable residuals in the final steel. This is where DRI scores over scrap. It is totally free from all the above undesirable elements. In basic open hearth steel making, refining begins with the bath containing about 1% excess carbon, often referred to as the opening carbon, in order that evolution of CO following the oxidation of carbon provides the necessary agitation for homogenization of the bath as well as for enhancing the reaction rates. In electric arc furnace steel making also, the initial bath carbon is maintained at about 0.3% above the final carbon specification during oxidizing refining. However, stirring is absent during refining under a reducing slag, and some other stirring technique, use of mechanical stirrers called rebels, is required. Now let us discuss about the advances in electric arc furnace steel making. Advances are the developments which have been done in the electric arc furnace steel making technology. So let us describe all of them in detail. There have been several advances in electric arc furnace technology which have allowed the electric arc furnace to compete successfully with the integrated production route. Majority of these have dealt with increases in productivity leading to lower cost of steel production. Present day electric arc furnaces can produce any type of steel grades which include the general purpose construction steel grade, the titanium niobium ultra low carbon steel for automotive body parts having a carbon specification of less than 0.0035% in order to optimize formability, the line pipe steel for gas distribution, which is a very demanding grade as the combination of high strength and high fracture toughness demands extremely low levels of impurities like phosphorus, sulfur, hydrogen, oxygen and nitrogen, and the engineering steel, which is a heat treatable low alloy steel grade. It contains considerable chromium and molybdenum additions. The developments in the electric arc furnace technologies since 1965 have promoted lower electric energy consumption, shorter tap-to-tap time, and less electrode consumption. Electric arc furnace size has enlarged up to 350 ton maximum, which together with the shortening of tap-to-tap time made possible to have more than 1 million tons per annum capacity with just one furnace. Electric energy consumption with 100% scrap operations has decreased to 350 kWh per ton. Chemical energy increased at levels not far from those of basic oxygen steelmaking processes. Refractory consumption has fallen down because of the replacement by cooled roof and panels, foaming slag, and refractory quality improvement. Power off time is now less than 10 minutes for the best operated furnaces. For a large number of electric arc furnaces, average electrode consumption is around 1.43 kilograms per ton. The present day ultra high power electric arc furnace has several sub-processes which have contributed to its remarkable productivity and efficiency. The phenomena which occur in the furnace include: first, heating of the scrap by the oxy-fuel burners, melting of the scrap by the electric arcs, liquid slag formation. Next comes oxygen and carbon injection for foaming of the slag. Next, movement of the scrap pieces during melting. Sixth one is oxygen lancing for scrap cutting and decarborization. Seventh is chemical reactions between slag and metal. And eighth one is post combustion of the CO, carbon monoxide, evolved from the reactions. These phenomena are interrelated, so that changes in operational practices probably change more than one of these phenomena. This makes the prospect for process control very challenging. The shift towards electric arc furnace steel making has been accompanied by technical advances which have allowed large decreases in power requirements and increased productivity. Some of the major technical advances are: first, foaming slag practice, in which a foaming slag is used to bury the arc and reduce refractory damage and heat loss from the arc region. Next is hot sheet operation, in which liquid steel is left in the bottom of the furnace to assist in the melting of fresh solid feed entering the furnace. Next is post combustion, in which CO generated during decarbonization is burned through oxygen injection from lances inside the furnace, and the energy liberated is used either in heating the bath directly or preheating the incoming feed materials. Fourth one is oxy-fuel burners, in which auxiliary burners are used to improve melting rates and to provide more than even heat distribution throughout the furnace. Fifth is preheating of scrap, in which a number of scrap preheating systems utilizing the heat associated with the exhaust gases have been developed, some based on batch bucket systems and others on continuous shaft systems. And sixth one is furnace electrics, where large improvements in control and energy efficiency have been accompanied the development of power supplies with higher operating voltages. Now let us describe and discuss about the equipments used in electric arc furnace steel making. The increase in furnace electric power has been the key factor in the development of electric arc furnace technology. As in the 1960s, a common EAF power was 250 kVA per ton of liquid steel to 300 kVA per ton of liquid steel, while today standard ultra-high power electric arc furnaces have 900 to 1000 kVA per ton of liquid steels available in the transformers. These furnaces are equipped with water-cooled panels and EBT tapping. EBT is eccentric bottom tapping, which I will be discussing later. EBT stands for eccentric bottom tapping, a system of tapping which yields a uniform steel jet falling into the ladle with slag carryover controlled to a certain extent. The present day electric arc furnace includes three water-cooled parts, namely: first, roof, panels, and next is exhaust gas duct. Although some heat is lost due to the heat extraction by the cooling water, this design makes possible less refractory consumption, since they replace refractory linings and the use of high power. At the time the panels were first introduced, some fears arose on safety risks, but after realizing the cost advantages, almost all electric arc furnaces adopted them. The panels can be made of steel or copper, which have much longer life, and with different designs like conventionally flip and turn, etc. Recently, more attention has been paid to safety with water cooling. Firstly, to detect, limit and avoid the possibility of water leakage, and secondly, to cut the need of repairing work in the hot furnace. Exhaust gas analysis, when hydrogen is included, is useful tool to detect leakage. To limit leakage and maintenance work, solid cast or machined water pans have been introduced. Split shell with spray cooled upper shell means less risk as non-pressurized water tends to penetrate less in case of leakage. Today, electric arc furnace process is an essential part of steel making. Melting is the main task of electric arc furnace process, and it is accomplished by energy supply which includes both electric power and chemical energy. The electric power is supplied by the graphite electrodes, which is the main energy supplier. Chemical energy is supplied through several sources, which mainly include oxy-fuel burners and oxygen injection. At first glance, the basic processes of the electric arc furnace appear quite straightforward, consisting of simply providing enough electrical energy to heat and melt the steel scrap. However, the whole process takes place under conditions of extreme temperature, which complicate maintenance of the furnace and the correction of any problems. For example, to preserve the refractory lining in the furnace, water cooling panels are built in the furnace walls. Without careful control, these can overheat and the process temperature has to be adjusted accordingly. During the process overhaul, the electrical input has to be balanced to make the best use of the power supply, which is controlled by the operator. The electrical, the electrical power is distributed among the three electrodes which melt the scrap by creating an arc between themselves and the scrap due to the resistance offered by the charged materials in the flow of electricity, which in turn generates heat. The electrodes are consumed during the process with a progressive wear by individual rate during power on. Some adjustments of the electrode positions need to be done to make sure that all three electrodes are in contact with the material so that energy is efficiently transferred. The electrodes hold brittle properties, that is limited mechanical toughness, and are consumables with a high cost. Hence, the electrodes need to be handled very carefully. If the furnace is filled with an excessive amount of coarse scrap, the electrodes need to be lowered very carefully in order to avoid expensive breakages. The electrodes progressively wear during heating and melting, and measures have to be taken to avoid shock electrodes. These are examples of some of the several events which can arise during the electric arc furnace process. I hope we are going so far so good and everything is clear to you all. Moving on, conventional electric arc furnaces today have 30 to 50% of their energy requirements met by the chemical energy, and it appears that the scrap melting is rather to be flexible in respect to from where the energy comes from. This is a distinct advantage of electric arc furnace steel making for several reasons. This has led the equipment manufacturers to develop a number of new furnaces which have improved energy efficiency and or flexibility. Now let us discuss about the raw materials used in electric arc furnace steel making technology. The main raw materials for electric arc furnace steel making is steel scrap. Today, the electric arc furnace is the most common way to recycle steel from scrap. There is a broad variety of steel scraps, both in terms of composition, from plain carbon steels through to highly alloyed tool steels, and geometry, from finely shredded sheet through to large beams. By melting the scraps in the electric arc furnace with the help of electrodes and an electric current, new functional steel can be produced from old products. Instead of deploying ore-based raw material resources, basic steel elements and valuable alloy steels can be reused, which is beneficial from both an economic and environmental point of view. Scrap is energy intensive and valuable commodity and comes primarily from three main sources, namely first, reclaimed scrap, also known as obsolete scrap, which is obtained from old cars, demolished buildings, discarded machinery, and domestic objects. Second, industrial scrap, which is also known as prompt scrap, and third one is revert scrap, which is also known as internal or home scrap, which is generated within the steel making and forming processes. Example, crop ends from rolling operations and metallics losses in slag, etc. The later two forms of scrap tend to be clean, that is, they are close in chemical compositions to the desired liquid steel composition and have hence are ideal for recycle. Reclaimed or obsolete scrap frequently has a quite variable composition and quite frequently contains contaminants which are undesirable for steel making. Levels of residual elements such as chromium, molybdenum, copper, stannum, and nickel are high in obsolete scrap and can affect casting operations and product quality if they are not diluted. Hence, a production shop which has a need for very low residual levels in the steel is forced to use higher quality prompt scrap but at a much higher cost. The alternative is to use a combination of the contaminated obsolete scrap along with what are normally referred to as clean iron, that is clean iron units or virgin iron units. These are materials which contain little or no residual elements. Clean iron units are typically in the form of direct reduced iron, that is DRI, hot briquetted iron HBI, iron carbide, liquid iron, hot metal, and pig iron. It is possible to use lower grade scrap which contains residual elements if this scrap is blended with clean iron units so that the resulting residual levels in the steel following melting meet the requirements for flat rolled products. Obsolete scrap is much more readily available than prompt scrap and hence the demand of clean iron units is always there. There are electric arc furnaces in which 100% steel scrap is the most common charge. The situation is not the same in all the electric arc furnaces in which alternative materials like DRI, HBI, hot metal and pig iron take part in the charge. Worldwide, scrap covers around 75% of the metallics for electric arc furnaces, while DRI and HBI covers around 15% and the balance is covered by hot metal and pig iron. It is well known that DRI melting consumes more electric energy than scrap. I repeat, this is an important aspect. It is well known that DRI melting consumes more electric energy than scrap. This has to do with the presence of acid gain in the iron ore, which follows to DRI and is then to be neutralized by lime addition and increased amount of slag compared with conventional melting of scrap. A high percentage of metallization helps in keeping energy consumption under control. Inherent to the coal-based direct reduction process is the low carbon content in DRI compared with gas-based DRI, 0.1% coal-based against around 2% for gas-based DRI. Carbon in the DRI is important since some of this carbon means an external energy source which combined with the oxygen injection in the electric arc furnace promotes a natural slag forming by the CO produced by the reaction of unreduced iron oxide and carbon in the DRI, which helps to decrease the electric energy consumption. In the electric arc furnaces, where the charge consists of 100% DRI or HBI, the charging is done through the fifth hole. Charging of high proportion of hot metal or pig iron in the electric arc furnace is practiced in some of the electric arc furnaces. In addition to classification of scrap into the above three groups, scrap is also classified based on its physical size, its source, and the way in which it is prepared. For example, the categories normally used are number 1 bundles, number 1 factory bundles, number 1 shredded, number 1 heavy melt, number 2 heavy melt, number 2 bundles, number 2 shredded, bushlings, turnings, shredded auto, structural, plate 1 meter, structural plate 1.5 meter, rail troughs and rail wheels, etc. In addition to the residual elements contained in the scrap, there are also several other undesirable components including oil, grease, paint, coatings, zinc coatings, water, oxidized material and dirt. The lower the grade of scrap, the more likely it is to contain higher quantities of these materials. As a result, this scrap can be cheaper, but the yield of liquid steel can be considerably lower than that achieved when using a higher grade scrap. In addition, these undesirable components can result in higher energy requirements and environmental problems. Hence, the decision for scrap mix is to be used within a particular production shop frequently depend on several factors including availability, scrap cost, melting cost, yield, and the effect on operations based on scrap density, oil and grease content, etc. In practice, majority of the production shops buy several different types of scrap and blend them to get the most desirable effects for electric arc furnace operations. Carbon is necessary for the production of steel. Carbon is one of the key elements which give different steel grades their properties. Carbon is also important in steel making, refining operations and can contribute a sizable quantity of the energy required during the steel making process. In basic oxygen steel making processes, carbon is present in the hot metal which is produced in the blast furnace. In the electric arc furnace steel making, some carbon is available in the scrap feed in DRI, HBI or other alternative iron furnace feeds. The quantity of carbon contained in these electric arc furnace feeds is normally considerably lower than that contained in the hot metal, and hence some additional carbon is needed to be charged to the electric arc furnace. In the past, carbon was charged to the electric arc furnace to ensure that the melt-in carbon levels was above the level desired in the final product. As higher oxygen utilization has developed as standard electric arc furnace practice, more carbon is needed in electric arc furnace steel making process. The reaction of carbon with oxygen within the bath to produce CO results in a considerable energy input to the process and has led to substantial reductions in electrical power consumption. The generation of CO within the bath is also a key to achieving low concentrations of dissolved gases, that is nitrogen and hydrogen, in the steel, as these are flushed out with the CO. In addition, oxide inclusions are flushed from the steel into the slag. In oxygen injection operations, some iron is oxidized to FeO, that is ferrous oxide, and goes to the slag. Oxy-fuel burner operations also result in some scrap oxidation, and this also goes to the slag once the scrap melts in. Dissolved carbon in the steel reacts with FeO at the slag or bath interface to produce CO and recover iron units to the bath. The quantity of charged carbon needed is dependent on several factors, which includes: first, carbon content of scrap feed; next, projected oxygen consumption; next is desired carbon at the tapping, and fourth one is the economics of iron yield compared with carbon cost. In general, the quantity needed corresponds to a E by O2 balance, as the furnace operator tries to maximize the iron yield. Typical charge carbon rates for medium carbon steel production lies in the range of 2 kg per ton of liquid steel to 12 kg liquid steel. Hello? The three types of carbonaceous materials which are normally used as charged carbon are: first, anthracite coal; second, metallurgical coke; and third, green petroleum coke. Anthracite coal typically has moisture content of 3% to 8%, ash content of 11% to 18%, and sulfur content of 0.4% to 0.7%. The high variation in ash content translates into wide variations in fixed carbon content, and hence for use in electric arc furnace, the ash content is to be kept to a minimum. The ash consists primarily of silica, that is SiO2. Hence, increased ash input to the electric arc furnace needs additional lime addition in order to maintain the desired basicity ratio in the slag. The best grades of anthracite coal have fixed carbon contents of 87 to 89%. Low grade anthracite coals can have fixed carbon levels as low as 50%. Anthracite coal is available in a wide variety of sizes ranging from 100 mm to 200 mm down to 1.2 mm to 100 mesh. The most popular sizes for use as charged carbon are of nut size, that is 20 mm to 40 mm, pea size 15 mm to 20 mm, and buckwheat size, that is 8 mm to 15 mm. Metallurgical coke is produced primarily in integrated steel plants and is used in the blast furnace. However, some coke is used as charged carbon in electric arc furnace. Normally, metallurgical coke has a composition consisting of moisture content 1 to 2%, volatile matters 1 to 2%, ash content 9 to 12%, fixed carbon content 86 to 88%, and sulfur content 0.88 to 1.2%. Normally, coke breeze with a size of -10 mm is used as charged carbon. Coarser materials can be used but has higher cost. Green petroleum coke is a byproduct of crude oil processing. Its properties and composition vary considerably and are dependent on the crude oil feedstock from which it is derived. Several coking processes are used in commercial operation and these produce considerably different types of petroleum coke. Sponge coke results from delayed coking operations and is porous in nature. It can be used as a fuel or can be processed into electrodes or anodes depending on the sulfur content and impurity levels. This material is sometimes available as charged carbon. Needle coke is produced using a special application of the delayed cooking process. It is made from high-grade feedstocks and is the prime ingredient for the production of carbon and graphite electrodes. This material is normally very expensive to be used as charged carbon in electric arc furnaces. Shock coke is a hard, pebble-like material resulting from delayed cooking operation under conditions which minimize coke byproduct generation. It is normally used as a fuel and is cost competitive as charged carbon. Fluid coke is produced in a fluid cooking process by spraying the residue onto hot coke particles. It is normally high in sulfur content and is used in anode baking furnaces. It can also be used as a recarburizer if it is calcined. So gentlemen, I hope we are going so far so good and moving ahead. Let us now discuss the operation of electric arc furnace. The electric arc furnace is a batch melting process which produces batches of liquid steel known as heats. The tap-to-tap cycle of the electric arc furnace is made up of several steps consisting of furnace charging, melting, refining, deslagging, tapping, and last but not the least, furnace turnaround. The present day electric arc furnaces aim for a tap to tap time of less than 60 minutes. Some electric arc furnaces with twin shells are achieving tap to tap times of 35 to 40 minutes. Today, a large number of electric arc furnaces operate with the condition called hot heal, meaning that almost 15% to 20% of metal from the previous heat has remained at the bottom of furnace after tapping. Hot heal increases productivity by allowing use of high electric power since it decreases the possibility of damaging refractory by powerful arcs and it also affects the melting rate of the scrap. Furnace charging. The first step in the production of any heat is to select the grade of steel to be made. Normally, a schedule is developed prior to each production shift. Hence, the operators, normally called the melters, know in advance the schedule for their shift. The scrap yard operator prepares buckets of scrap according to the needs of the electric arc furnace operator. Preparation of the charge bucket is an important operation not only to ensure proper melting chemistry but also to ensure good melting conditions. The scrap is to be layered in the bucket according to size and density to promote the rapid formation of a liquid pool of steel in the hearth while providing protection for the side walls and roof from electric arc radiations. Other considerations include minimization of scrap cavings which can break electrodes and ensuring that large heavy pieces of scrap do not lie directly in front of burner ports which results in the blowback of the flame onto the water-cooled panels. The charge can include lime and carbon or these can be injected into the furnace during the heat. Many operators add some lime and carbon in the scrap bucket and supplement this with injection. The first step in any tap-to-tap cycle is charging of the scrap in electric arc furnace. The roof and electrodes are raised and are swung to the side of the furnace to allow the scrap charging crane to move a full bucket of scrap into place over the furnace. The bucket bottom is normally of a clam shell design, that is, the bucket opens up by retracting two segments on the bottom of the bucket. The scrap falls into the furnace and the scrap crane removes the scrap bucket. The roof and electrodes swing back into place over the furnace. The roof is lowered and then the electrodes are lowered to strike an arc on the scrap. This commences the melting portion of the cycle. The number of charge buckets of scrap needed to produce a heat of steel is dependent primarily on the volume of the furnace and the scrap density.
Before proceeding, if you like my content and have not subscribed to my channel till now, then please subscribe to my channel so that you can get watch all the videos available in my channel list, and also press this bell icon so that you can get the notification of new videos promptly and don't miss anything. In case you want to thank me and support me so that I can get further motivation to do better in future, you can just simply send me this special thanks, super thanks, by selecting any of this amount of your choice, whatever you feel like suitable to you. You can just buy this and send to me. This will help me to do further better. You can select any of the payment methods of your choice and then send me. This will motivate me to do further better in future. Thank you.
I hope my message in the previous slide is very much clear to you all. So please do support me so that I can survive and I can contribute for you for your learning and development and growth and continue making new videos from time to time and providing you contents. So please do support me, and now let's move on. Present-day electric arc furnaces are designed to operate with a minimum of back charges. This is advantageous since charging is a dead time where the electric arc furnace does not have power on and hence is not melting. Minimizing of these dead times helps to maximize the productivity of the electric arc furnace. In addition, energy is lost every time the furnace roof is opened. For each occurrence, the energy loss is between 10 kWh per ton to 20 kWh per ton. Majority of the electric arc furnace operators aim for 2 buckets to 3 buckets of scrap per heat and they attempt to blend the scrap for meeting this requirement. Some electric arc furnace operations achieve a single bucket charge also. Continuous charging operations such as Conch steel and the first shaft furnace eliminate the charging cycle. Now let us come to the next step, that is melting. The melting period is the heart of electric arc furnace operations. The electric arc furnace has evolved into highly efficient melting equipment and the present day designs are focused on maximizing the melting capacity of the electric arc furnaces. The heat needed to melt steel scrap is provided by electric arcs created between the electrodes and the scrap in the furnace. The electrical power of normal electric arc furnaces lies in the range of 50 megawatt to 120 megawatt depending on the size of the furnace. Melting of the scrap occurs at a temperature range of 1500 degrees Celsius to 1550 degrees Celsius depending upon the composition of the steel scrap. Melting is accomplished by supplying energy to the furnace interior. This energy can be electrical or chemical. Electrical energy is supplied through the graphite electrodes and is normally the largest contributor in melting operations. Initially, an intermediate voltage tap is selected until the electrodes bore into the scrap. For accelerating the boring, normally light scrap is placed on top of the charge. Around 15% of the scrap charge is melted during the initial boring period. After a few minutes, the electrodes have penetrated the scrap sufficiently so that a long arc high voltage tap can be used without fear of radiation damage to the roof. The long arc maximizes the transfer of power to the scrap and a liquid pool of metal is formed in the furnace hearth. At the start of melting, the arc is erratic and unstable. Wide swings in current are observed which are accompanied by rapid movement of the electrodes. As the furnace atmosphere heats up, the arc stabilizes and once the liquid pool is formed, the arc becomes quite stable and the average power input increases. Although ultra-high power furnaces are used, fast melting by using only electric power is difficult and not the most economic practice either. Importing extra energy and assisting melting technique can greatly accelerate scrap melting and bring economic benefits. Accordingly, the present state of the art in electric arc furnace steel making is to use as much as possible chemical energy besides electric energy to accommodate tap to tap times to the pace of the downstream continuous casting process. Chemical energy is to be supplied through several sources including oxy-fuel burners and oxygen lances. In the oxy-fuel burners, fuel gas is burned using oxygen or a blend of oxygen and air. Heat is transferred to the scrap by flame radiation and convection by the hot products of combustion. Heat is transferred within the scrap by conduction. Large pieces of scrap take longer to melt into the bath than smaller pieces. In some of the electric arc furnaces, oxygen is injected through a consumable pipe lance to cut the scrap. The oxygen reacts with the hot scrap and burns iron to produce intense heat for cutting the scrap. Once a liquid pool of steel is generated in the furnace, oxygen can be launched directly into the bath. This oxygen reacts with several components in the bath which include carbon, iron, aluminium, silicon, manganese and phosphorus. All of these reactions are exothermic in nature, that is, they generate heat and supply additional energy to aid in the melting of the scrap. The metallic oxides which are formed end up in the slag. The reaction of oxygen with carbon in the bath produces CO, that is carbon monoxide, which either burns in the furnace if there is sufficient oxygen and or is exhausted through the direct evacuation system where it is burned and conveyed to the pollution control system. Once enough scrap has been melted to accommodate the second charge, the charging process is repeated. Once the final scrap charge is melted, the furnace sidewalls are exposed to intense radiation from the arc. As a result, the voltage is to be reduced. Alternatively, creation of a foamy slag allows the arc to be buried and protects the furnace shell. In addition, a higher quantity of energy is to be retained in the slag and is transferred to the bath, resulting in higher energy efficiency. One of the most perplexing aspects about scrap is the way it moves during the melting process, and this causes operational problems such as cave-ins in which the scrap suddenly collapses onto the electrodes. These events disrupt the electrical operation, necessitating the rising of the electrodes or in extreme cases precipitating breakage of the electrodes. Further, the solid scrap is introduced into a liquid steel pool when the charge is dropped into the liquid heel and also when scrap starts to cave in to the pool which is formed by the arcs during the melting process. Electric arc furnace operators frequently talk about icebergs or steel bergs that form by the bridging of several pieces of scrap which can take longer to melt than the individual pieces. However, it is difficult to understand the contributing factors to this problem. Once the final scrap charge is fully melted, flat bath conditions are reached. At this point, a bath temperature and sample is taken. The analysis of the bath chemistry allows the operator to determine the quantity of oxygen to be blown during the refining. At this point, the operator can also start to arrange for the tap bulk ferroalloy additions to be made. These quantities are finalized after the refining period. Now let us discuss about the next step, which is refining. After the scrap has been melted, the temperature is normally increased so that refining reactions can be carried out. Oxygen and carbon can be injected into the steel phase and slag phase respectively. I repeat, oxygen and carbon can be injected into the steel phase and slag phase respectively. That means oxygen to steel phase and carbon to slag phase. However, the reactions can also create products which are detrimental to the steel quality and which therefore need to be handled carefully. To do that, a slag is formed with the help of slag forming agents such as lime, calcined dolomite and fluorspar. Slag, having a lower density than steel, normally floats on the steel surface. In addition to absorbing impurities from the steel, the slag also protects the steel from the atmosphere. So these are the major advantages and functions of slag in steel making. In addition, it protects the furnace walls from the arcs, thereby increasing the electrical efficiency. It is hence of great importance to maintain a high slag quality and provide it with foaming properties. Slag properties like viscosity, sulfur capacity and phosphorus capacity, etc. vary with composition and temperature. One of the main tasks during the refining operation is to maintain adequate slag properties by adding slag forming agents such as lime, calcined dolomite and or fluorspar. That is why you might have probably heard that a best steel maker is the best slag maker. So my dear friends, do concentrate on making the best possible slag, then the steel will be made the best. Moving on, some of the metallic oxides which end up in the slag are acidic in nature. Hence, adding basic slag forming agents helps to keep the basicity of the slag at an appropriate level. High slag basicity, that is high CaO by SiO2 ratio, is also beneficial for the removal of phosphorus, but care is needed not to saturate the slag with CaO, as this leads to an increase in slag viscosity which makes the slag less effective. Refining operations in the electric arc furnace have traditionally involved the removal of phosphorus, sulfur, aluminium, silicon, manganese and carbon from the steel. In recent times, dissolved gases, especially hydrogen and nitrogen, have been recognized as a concern. Traditionally, refining operations are carried out following the meltdown, that is, once a flat bath is achieved. These refining reactions are all dependent on the availability of oxygen. Oxygen is launched at the end of meltdown to lower the bath carbon content to the desired level for tapping. Majority of the compounds which are to be removed during refining have a higher affinity for oxygen than that for the carbon. Hence, the oxygen preferentially reacts with these elements to form oxides which float out of the steel and into the slag. Decarbonization is carried out as a refining task. If the charge is 100% scrap, carbon in the metallic charge is relatively low. This is not the case when charging a high percentage of DRI, that is, if produced in a gas-based unit, HBI, hot metal or pig iron with carbon contents varying between 1.6 to 4.5%. Normally, due to the productivity reasons, electric arc furnace operators prefer to achieve a carbon content of around 0.05% before tapping. Lower contents can imply a too high oxidation level. An alternative strategy is catch carbon practice, in which carbon content is targeted at somewhat under the final value to be reached with ferroalloys addition. This practice can bring material savings in alloying and deoxidation, but needs strict individual process control for each heat. For this reason, it is not so good for productivity. Further, if final carbon is maintained high, dephosphorization can be a problematic. In the present day electric arc furnaces, especially those operating with a hot heat of liquid steel and slag retained from the previous heat, oxygen can be blown into the bath throughout the most of the heat. As a result, some of the melting and the refining operations occur simultaneously. Phosphorus and sulfur normally occur in the electric arc furnace charge in higher concentrations than are normally permitted in steel and are to be removed. Unfortunately, the conditions favorable for removing of phosphorus are the opposite of those promoting the removal of sulfur. Hence, once these materials are pushed into the slag phase, they can revert back into the steel. Phosphorus retention in the slag is a function of the bath temperature, the slag basicity, and the FeO levels in the slag. At higher temperatures or low FeO levels, the phosphorus reverts from the slag back into the bath. My dear friends, this is a very important information which is normally asked and is expected that a good steelmaker must know why phosphorus is reversed to the bath at low temperatures, at higher temperatures or at low FeO levels, and or how and why it reverts. So it is very much necessary to keep in mind. So I have provided these informations. I hope you like it. So now moving on. Phosphorus removal is normally carried out as early as possible in the heat. Hot heat practice is very beneficial for the removal of phosphorus, since oxygen can be launched into the bath while its temperature is quite low. Early in the heat, the slag contains high FeO levels carried over from the previous heat, hence aiding in the removal of phosphorus. High slag basicity, that is high CaO content, is also beneficial for the phosphorus removal, but care is to be taken not to saturate the slag with CaO, which leads to an increase in slag viscosity and hence makes the slag less effective. Sometimes torspar is added to help fluidize the slag. Stirring up the bath with inert gas is also beneficial, since it renews the slag or metal interface, hence improving the reaction kinetics. In general, if low phosphorus levels are a requirement for a particular steel grade, the scrap is selected to give a low level at melting. The partition of phosphorus in the slag to phosphorus in the bath ranges from 5 to 15. Normally, phosphorus is reduced by 20% to 50% in the electric arc furnace. Sulfur is removed mainly as a sulfide dissolved in the slag. The sulfur partition between the slag and metal is dependent on slag chemistry and is favored at low steel oxidation levels. Removal of sulfur in the electric arc furnace is difficult, especially in the present day practices where the oxidation levels of the bath is quite high. Normally, the partition ratio is between 3 and 5 for electric arc furnace operations. Majority of the electric arc furnace operators find it more effective to carry out desulfurization during the reducing stage of the steel making. This means that desulfurization is performed during tapping where a calcium aluminate slag is built and during ladle furnace operations. For reducing conditions where the bath has a much lower oxygen activity, distribution ratios for sulfur between 20 and 100 can be achieved. Control of the metallic constituents in the bath is important since it determines the properties of the final product. Normally, the operator aims at lower levels in the bath than are specified for the final product. Oxygen reacts with aluminium, silicon and manganese to form metallic oxides which are of the slag components. These metallics tend to react with oxygen before carbon. They also react with FeO resulting in a recovery of iron units to the bath. For example, Mn plus FeO gives to MnO plus Fe. Manganese is typically lowered to around 0.06% in the bath. The reaction of carbon with oxygen in the bath to produce carbon monoxide is important since it supplies a less expensive form of energy to the bath and performs several important refining reactions. In the present day electric arc furnace operations, the combination of oxygen with carbon can supply between 30 to 40% of the net heat input to the furnace. Evolution of CO is very important for slag foaming. Coupled with a basic slag, CO bubbles are trapped in the slag, causing it into foam and helping to bury the arc. This gives greatly improved thermal efficiency and allows the furnace to operate at high arc voltages even after a flat bath has been achieved. Burying the arc also helps to prevent nitrogen from being exposed to the air arc where it can dissociate and enter into the steel. If the carbon monoxide is evolved within the steel bath, it helps to strip nitrogen and hydrogen from the steel. Nitrogen levels in steel as low as 50 ppm, that is parts per million, can be achieved in furnace prior to tapping. Bottom tapping is beneficial for maintaining low nitrogen levels since tapping is fast and a tight tap stream is maintained. A high oxygen potential in the steel is beneficial for low nitrogen levels and the heat is to be tapped open as opposed to blocking the heat. At 1600 degrees Celsius, the maximum solubility of nitrogen in pure iron is 450 ppm. Typically, the nitrogen levels in the steel following tapping are ranging from 80 ppm to 100 ppm. Decarburization is also beneficial for the removal of hydrogen. It has been demonstrated that decarbonizing at a rate of 1% per hour can lower hydrogen levels in the steel from 8 ppm down to 2 ppm in 10 minutes. At the end of refining, a bath temperature measurement and a bath sample are taken. If the temperature is too low, power can be applied to the bath. This is not a big concern in the present day steel melting shops where temperature adjustment is carried out in the ladle furnace. For most steel making operations, refining in the electric arc furnace is limited to dephosphorization, decarbonization and temperature adjustment. Phosphorus in the charge can be at higher than usual levels for DRI and HBI, pig iron, hot metal depending on the iron ore source. Some steels require particularly low phosphorus levels to avoid too high ductile or brittle transition temperatures for tempering brittleness. From the equilibrium point of view, lower temperatures, high slag basicity and high oxidation of the bath favor dephosphorization. My dear friends, the conditions favoring dephosphorization are lower temperatures, high slag basicity and high oxidation of the bath. Please note it down. Slag and metal interaction is important from a kinetic point of view, but it is not always attainable in the electric arc furnace. Reversion of phosphorus from slag to steel can take place when heating to the aimed temperature close to the end of the process. Then, if there is some slag carryover to the ladle and steel and slag have a low oxidation level, phosphorus reversion is again possible. Hence, in such phosphorus critical cases, slag carryover to the ladle is to be carefully prevented. This can be done by slag detection, slag stopping system or by EBT, that is eccentric bottom tapping, which is stopped before the end of the steel. In such a hot heat practice, a considerable fraction of liquid steel is left in the furnace for the next heat. Hot heat practice not only prevents steel from rephosphorization but also speeds up the melting process. However, it has a smaller charge weight in the ladle as a drawback. The refining step normally does not need full power, which with already flat bath can be dangerous for the lining. At that time, the foaming of the slag is a must. For the slag to foam, the production of CO gas is necessary by means of injection of carbon and oxygen through lances or burners. For foaming purposes, several carbonaceous materials are useful depending on local cost and availability. These are anthracite, petroleum coke and coke grease, which I have already mentioned earlier in the presentation. I hope you remember that. In the EAF, the melt can flow due to mechanisms taking place during the melting process, but thermal stratification does not disappear. So it takes normally a long time for large pieces of scrap to be melted. Concentration gradient in the bath has also been reported, which causes the reaction rates in the bath to decrease, and also the reactions do not take place uniformly in all parts of the bath. Thermal stratification is a more common problem in ultra high power furnaces where there is a high superheat. Hence, it is important that the melt dripping down from the top is convected to reduce stratification. These are some of the important practical aspects which are dealt in the day-to-day furnace operations. So I have put them for your reference and consideration. So I think it is a good information, good piece of information. Okay, moving on. The idea of stirring or forced convection in the bath has been introduced some years ago to improve the melt flow and eventually decrease the energy consumption. The first electromagnetic coils were used in a laboratory scale in 1933, and the studies showed that the flow velocities for stainless steel are lower than the carbon steels when electromagnetic stirring was used. It has been shown that stirring is more important in production of low carbon steels, since when the content of carbon goes down to below 0.2%, decarbonization due to oxygen blowing is not that effective. Hence, a powerful driving force is needed to transfer carbon to the reaction zone where oxygen is blowing. In forced convection, an external driving force is used to make the fluid flow, and the magnitude of velocity and rate of heat transfer increase in comparison to the natural convection. CO bubbles formed during formation of the foaming slag contribute to bath circulation, but an additional amount of gas can be injected into the bath to increase the intensity of bath stirring. Inert gas like nitrogen, argon, or mixture of both can be injected through tuyeres or porous plugs submerged within the bottom refractory of the furnace. The number of tuyeres or plugs used is dependent on their size as well as the size of the furnace. The blowing is normally done with the low intensity of 0.1 cubic meter per ton minute. Next phase is deslagging. Deslagging operations are carried out to remove impurities from the furnace. During the melting stage and refining operation, some of the undesirable materials within the bath are oxidized and enter the slag phase. It is advantageous to remove as much as phosphorus into the slag as early in the heat as possible, that is, while the bath temperature is still very low. I hope you remember that I have already described this thing in detail in the previous slides. The furnace is tilted backwards and slag is poured out of the furnace through the slag door. Removal of the slag eliminates the possibility of phosphorus reversion. During the slag foaming operations, carbon can be injected into the slag where it reduces FeO to metallic iron and in the process produces CO, which helps to foam the slag. If the high phosphorus slag has not been removed prior to this operation, phosphorus reversion occurs. During slag foaming, slag can overflow the sill level in the EAF and flow out of the slag door. Below table 1 shows the typical constituents of the EAF slag. So this particular table shows the typical constituents of the electric arc furnace slag. You can pause this video and observe the different things available, different constituents in the slag. Okay, moving ahead. So far so good. So next operation is tapping. Once the desired steel composition and temperature are achieved in the furnace, the tap hole is opened for tapping the heat. Tapping can either be through a spout or through a tap hole positioned at the bottom of the furnace. In case of spout tapping, the furnace is tilted and the steel pours into a ladle for transfer to the next batch operation, normally a ladle furnace. During the tapping of process, bulk alloy additions are made based on the batch analysis and the desired steel grade. Deoxidizers can be added to the steel to lower the oxygen content prior to further processing. This is normally referred to as blocking the heat or killing the steel. Common deoxidizers are silicon in the form of ferrosilicon or silicomanganese and aluminium. Majority of the carbon steel operations aim for minimal slag carryover. A new slag cover is built during tapping. For ladle furnace operations, calcium aluminate slag is a good choice for the sulfur control. Slag forming compounds are added in the ladle at tapping so that a slag cover is formed prior to transfer to the ladle furnace. Additional slag materials can be added at the ladle furnace if the slag cover is insufficient. Next, last but not the least of the steps is furnace turnaround. Furnace turnaround is the period following completion of tapping until the furnace is recharged for the next heat. During this period, the electrodes and roof are raised and the furnace lining is inspected for refractory damage. If necessary, repairs are made to the hearth, slag line, tap hole and spout. In the case of a bottom tapping furnace, the tap hole is filled with sand. My dear friends, I hope you can understand and conceptualize that the hot repairs are done during the furnace when it is in hot condition, and during this furnace turnaround time, normally they are called patching work, so that the furnace doesn't get deteriorated and the refractory lining is repaired while the furnace is hot. Okay. So now repairs to the electric arc furnace are made using the knitting refractories or mud slingers. In the majority of the present day electric arc furnaces, the increased use of the water-cooled panels has reduced the quantity of patching or fettling needed between the heats. Several operators now switch out the furnace bottom on a regular basis, that is 2 weeks to 6 weeks, depending on the different companies from plant to plant and operator's experience, and perform the hearth maintenance offline. This reduces the power of time for the electric arc furnace and maximizes the furnace productivity. Furnace turnaround time is normally the largest dead time, that is power of time period, in the tap to tap cycle. So we must always should try to keep the furnace turnaround time as low as possible. With advances in furnace practices, this has been reduced from 20 minutes to less than 5 minutes in some newer installations. So now let us discuss about the chemical reactions in the electric arc furnaces, steel making technology. During and after the meltdown of the raw materials, several compounds and elements begin to react with each other. In order to reach the required quantities of the respective elements in the steel, the reaction processes are to be facilitated by injection of carbon and oxygen through the lungs. By injecting carbon into the steel phase and oxygen into the slag phase, CO bubbles are formed and a foaming slag is created. One of the oxide reactions forms CO gas, which is especially important for the formation of a foaming slag. Carbon injection into the slag phase through the lungs creates CO bubbles through a reaction with oxygen. These bubbles then help to cause the slag to foam. A foaming slag protects the liquid steel from reacting with the atmosphere and also increases the electrical efficiency by burying the arc from the electrodes. This provides thermal efficiency and allows the furnace to operate at higher voltages without damaging the furnace walls and roofs. Burying the arc also helps to prevent nitrogen from being exposed to the arc where it can dissociate and enter into the steel. Due to the high affinity of oxygen to the elements such as aluminium, silicon, chromium, carbon, phosphorus and iron, metallic oxides are easily formed, and because of their relatively low density, these float up to the slag face. All of these reactions are exothermic, that is, they provide heat to the system and hence supply additional energy to melting and heating the scrap. The thermodynamic and kinetics of the process assumes that the reaction which provides the lowest dissolved oxygen content controls the desired oxygen activity in the steel. The reactions that are highly exothermic are: first, 2Al plus 3O is equal to 2Al2O3. Next is C plus O, this gives CO. Third one is 2Cr plus 3O, this gives Cr2O3. Next is Fe plus O, this gives FeO. And Si plus 2O, this gives SiO2. All these reactions are exothermic in nature, as I have described earlier. There are several chemical reactions which are taking place during the steel making in the electric arc furnace. These reactions are between charged materials and elements and substances added to a melt in order to prepare steel of a required composition in the electric arc furnace. These chemical reactions generate a lot of chemical energy, which can also improve the efficiency and reduce the time of electric arc furnace process. In electric arc furnaces, chemical reactions can affect the temperature of the steel, which is one of the most important factors for the steel making. The chemical reactions taking place in the electric arc furnace can be grouped into four categories, namely: first category is chemical reactions of scrap components. Second category is chemical reactions proceeding on adding fluxes. Third is chemical reactions during deoxidation, and fourth group is chemical reactions with alloy additions. Now first consider the chemical reactions of scrap components. The chemical reactions of scrap components are listed below. First one is 2Fe plus 3O, this gives Fe2O3. Next, Fe plus O, this gives FeO. C plus O, this gives CO. Si plus 2O, this gives SiO2. Mn plus O gives MnO. 2P plus 5O gives P2O5. And 2Cr plus 3O gives Cr2O3. Next group is chemical reactions proceeding on adding fluxes. The chemical reactions proceeding on adding fluxes are: first, CaO plus S, this gives CaS plus O. Next is CaCO3 gives dissociates into CaO plus CO2. Next reaction is MgCO3, which dissociates into MgO plus CO2. And next one is 2Al plus 3O, this gives Al2O3. Next is chemical reactions during deoxidation. The chemical reactions during deoxidation are: first, Mn plus O, this gives MnO. 2Al plus 3O, this gives Al2O3. Si plus 2O, this gives SiO2. 2Fe plus 3O, this gives Fe2O3. Fe plus O, this gives FeO, and C plus O, this gives CO. Now considering chemical reactions with allying additions, the chemical reactions with allying additions are first Mn plus O, this gives MnO, 2Fe plus 3O, this gives Fe2O3, Fe plus O, this gives FeO, Si plus 2O, this gives SiO2, C plus O, this gives CO, 2P plus 5O, this gives P2O5, CO plus S, this gives CAS plus O, 2Al plus 3O, this gives Al2O3, 2Cr plus 3O, this gives Cr2O3, Zn plus O, this gives ZnO, and 2B plus 3O, this gives B2O3. Next, chemical energy is very important for melting steel in an electric arc furnace. Energy of exothermic reactions is a secondary energy source in an electric arc furnace. However, these forms of energy are basic in an electric arc furnace. Electrical energy comprises of the order of around 60% of the overall expenditure, and chemical energy of the order of around 30% of energy required in an electric arc furnace. The balance energy comes from the input through oxy-fuel burners. Chemical energy is introduced by oxygen, carbonaceous materials, and fuel gases more and more through injectors rather than lances. The energy generating reactions are C plus half O2, this gives CO, and it generates 2.55 kWh per kg of carbon. C plus O2, this gives CO2, generating 9.1 kWh per kg of carbon. CO plus half O2, this gives CO2, generating 2.81 kWh per kg of carbon. And next is Fe plus half O2, generating FeO, 1.32 kWh per kg of iron. I hope these reactions are very clear to you all and don't have any problem in understanding them. Certain grades of steel, such as those used for gas and oil pipelines, need very low levels of sulfur to provide better welding and forming properties. Desulfurization is driven by an exchange of sulfur between the liquid steel and the slag. The reactions which take place are governed by the dissolved content of aluminium and sulfur in the steel and the content of CaO, Al2O3 and calcium sulfide, that is CaS, in the slag. Normally, this is described by the reaction 3CaO plus 2Al plus 3S gives rise to 3CaS plus Al2O3. In practice, desulfurization in the electric arc furnace is achieved by first adding a synthetic CaO-based desulfurizing slag at furnace tapping, and next aluminium deoxidizing the steel to very low oxygen activity. Otherwise, the aluminium reacts preferentially with oxygen. Now let us discuss the very much important role of slag. It is very important to learn and know about the role of slag. Very important. So let us discuss. An important part of steel making is the formation of slag, which floats on the surface of the liquid steel. As I have already mentioned that it is said that a good steel maker is a good slag maker. So let us further learn and know the importance of slag. Slag normally consists of metal oxides and acts as a destination for oxidized impurities. Protection of cooling panels and refractories, arc stability, Dephosphorization, thermal insulation, and heat transfer are some of the expected tasks for the slag. The main slag formers in the electric arc furnace are lime, calcined dolomite, oxides in scrap, gangue in DRI, oxidation products from metallic charge, ash of carbonaceous additions, MgO picked up from refractories, as well as the slag remaining from the previous heat. So these are the main sources of slag formers. Some plants recycle scale or other waste, hence adding to the slag. The main EAF slag components are CaO, SiO2, FeO, and MgO, and other components are Al2O3, MnO, and P2O5. Majority of the electric arc furnaces use basic refractories, and as a result, it is necessary to maintain a basic slag in the furnace in order to minimize the refractory consumption. Slag basicity has also been shown to have a major effect on slag foaming capabilities. Hence, lime is to be added both in the charge and also through injection directly into the furnace. Line additions practices can vary greatly due to the variations or variances in scrap composition. As elements in the bath are oxidized, example phosphorus, aluminium, silicon, manganese, etc., they contribute acidic components to the slag. Hence, basic slag components are to be added to offset these acidic contributions. If silica levels in the slag are allowed to get too high, considerable refractory erosion results. In addition, FeO levels in the slag increases since FeO has greater solubility in higher SiO2 slags. This can lead to higher yield losses in the electric arc furnace. The generation of slag also allows these materials which have been stripped from the bath to be removed from the steel by pouring slag out of the furnace through the slag door which is located at the back of the electric arc furnace. I hope you can visualize the picture which I have already shown in previous slides. This is known as deslagging or slagging off. If the slag is not removed but is instead allowed to carry over to the ladle, it is possible for the slag reversion to take place. This occurs when metallic oxides are reduced out of the slag by a more reactive metallic present in the steel. When steel is tapped, it is frequently killed by adding either silicon or aluminium during tapping. The purpose of these additions is to lower the oxygen content in the steel. If, however, P2O5 is carried over into the ladle, it is possible that it reacts with the alloy additions producing SiO2 or Al2O3 and phosphorus, which goes back into solution in the steel. Sometimes magnesium lime is added to the furnace either purely as MgO or as a mixture of MgO and CaO. Basic refractories are predominantly MgO, hence by adding a small quantity of MgO to the furnace, the slag can quickly become saturated with MgO and hence less refractory erosion is likely to take place. In the ternary diagram of figure shown in the next slide, including MgO saturation lines, it is possible to evaluate MgO needed for saturation of a slag of a given basicity and FeO content. Control of foaming slag remains a matter of continuous development. Majority of the electric arc furnaces incorporate tools to evaluate slag foaming based on noise, vibration and harmonics. In majority of cases, this is used as an offline help for the furnace operator. But some electric arc furnaces have recently introduced online control of the carbon and oxygen injection for slag forming based on the mentioned measurements. So this figure describes the isothermal cross-section of CaO, SiO2 and FeTO diagram. So you can pause the video and observe this diagram very carefully. Okay, let's move on. A mass balance based on the chemistry and weight of those slags formers is helpful for the comparison with measured chemistry for a better understanding of attack on refractory linings, line fines lost to the exhaust gas, incidence of changes in weight, chemistry of additions, etc. For foaming purposes, it is important to maintain slag basicity, that is percentage of CaO divided by percentage of SiO2 between 1.2 to 2.5. To decrease the need of MgO for slag saturation, slag basicity is to be maintained at least to 2. Dear friends, I am providing you all the informations free of cost which are available in my YouTube channel. So do help me by watching all my videos. Do subscribe my channel. Regularly visit and repeatedly visit my channel. Do watch all my videos, contents, like the content, share with your friends, and so that I also get motivated from each one of you as you subscribe to my channel. I am very much thankful to all my subscribers who believe in me, have subscribed my channel, and like my content. So to motivate me further, please do subscribe my channel, increase the subscriber count, share with your friends so that others can also gain the knowledge. And my dear friends, all if you subscribe my channel, this will motivate me to do further better. So I hope you like the content and found the video worth. So again request you to please don't forget to like, share and subscribe the channel. Also remember to press the bell icon so that you can get the notification of the new videos promptly. My dear friends, here if you want to advertise about your product, services or company or anything else for gaining popularity in my channel, so you can contact me so that I can put your content for advertisement in my videos, forthcoming videos. So it will be a good platform to advertise. So do contact me as soon as possible. Thank you very much for watching this video till the end, and I am very much again thankful to all of you who helped me, who believe in me, and please do visit my channel regularly and repeatedly. Thank you very much again. See you in the next video. Thank you.